first of all, that we're all in the right place. So hopefully you're coming to special topics in CMSE, the course on topological methods for the analysis of data. My name is Jose Pereira. I'm going to be your instructor for the semester. So I'm a faculty member in CMSE, Computational Mathematics, Science and Engineering, and I'm also a faculty member in the Department of Mathematics. So my brain works in sort of both worlds. So what I want to do today is I want to give you sort of an overview or sort of the flavor for what the class has to offer, and then we'll go through the structure and all the sort of administrative stuff, okay? So before I begin, let's just go around the room and just tell me your name and what department you're from, okay? So start here.
Hi, I'm Luis. I'm in the math department.
Luis, what year are you?
Second year.
Second year math, okay?
I'm Jane.
Jane? Okay. Physics, cool. What year? Second year.
I'm Maria. Second year.
Second year physics, okay?
I'm Auden. I'm second year in mechanical engineering.
Okay, so math, physics, mechanical engineering. We're gonna jump over the other Luis. So he's gonna be recording some of the lectures, I forgot. So we're gonna try to put some video up on the course website. And we'll see how that experiment goes. So if you don't wanna be recorded for any reason, please send me an email and then we'll work it out. But hopefully it'll be a useful resource for everybody.
Oh, I'm Xiaoyan Li. I'm in environmental engineering. This is my fourth year.
Fourth year, okay?
I'm Josh, it's my second year in mechanical engineering.
Mechanical engineering?
Yes.
Josh. Okay. Yep.
I'm Sho. I am in the math program, second year.
Math department, second year, okay?
I'm Mili, and I'm second year in mechanical engineering department.
Okay, so we have a bunch of people from engineering, physics, and math.
I'm Manoj. I'm a second year in biomedical engineering.
Biomedical, okay. Different. Biomedical.
I'm Matt. I'm first year CMSE.
I'm Khalid, I'm fifth year computer science.
Computer science, cool. And?
I'm Joseph. I am actually finishing my undergraduate degree here this semester.
Okay, what departments? Physics and math. Okay, so cool. This is an interesting composition of the room. We have a bunch of people from engineering, math, and physics. So let me explain where we're going with the course, and hopefully it is what you were expecting. If not, you can still cancel it. So hopefully many people have heard about geometry. So if you look in the dictionary what geometry is, if you look at the Greek roots, you will see that it's earth and measure. And the idea is that you're using measurements to understand the world. That's what geometry is. And you do it through measurements like area, volume, perimeter, curvature, and angles. And you can, of course, create more sophisticated measures if the objects you want to measure are more complicated. But again, the main idea is understand the physical world and even the sort of scientific world through measurements. Okay? Topology, which is one of the words in the course description, is similar to geometry. But the difference is that we don't care so much about sizes, but we care about shapes. And the idea is the following. In topology, we think that two objects are similar if we can go from one to the other through continuous deformations without tearing holes or piecing together pieces of the space. So in that sense, is this working? Of course not. In that sense, a triangle is the same as a disk and the same as a square, because if you imagine that they're made out of sort of Play-Doh, you can stretch one into the other. And the typical joke is that a topologist cannot tell the difference between a donut and a coffee mug because you can go from one to the other through continuous deformations. Okay, so that's what topology is. On the one hand, geometry cares about rigid notions, and topology cares about shapes objects up to deformation. Okay? So why do we care about these ideas? So algebraic topology is one branch of topology. And what it does is it gives you computational methods to study shape, this sort of notion that sounds like very abstract. So let me tell you, or at least give you a flavor of how that is done. So, so let's say that I give you two shapes, a disk and an annulus, and you ask, can I go from one to the other without punching holes or piecing stuff in the space together? The intuition would be no, but you want to do that mathematically. Here's one way to do that. So one thing we can do to a surface is to triangulate it. So what does that mean? It means divide it into triangles with vertices, edges, and triangular faces. We don't care about the edges being straight, because remember, everything is up to deformations, okay? So once you have a triangulation of a space, you can count, and you can do things like counting the number of vertices in the triangulation. You can subtract the number of edges, and you can add the number of triangular faces. You can say that sounds ridiculous, but bear with me for a moment. So if you do that for these two spaces, you get that for the disk, you get 1. For the annulus, you get 0. Why is that important? There's this beautiful theorem due to Leonard Euler, back in the day. It says the following. If you start with a surface and you triangulate it, then the quantity number of vertices minus number of edges plus number of faces, that is called the Euler characteristic, that number is independent of the way you triangulated your space, right? So if you chose another triangulation with perhaps more vertices or more edges, you would get the same number. That's the first part of the theorem. And the second part of the theorem is that the number does not change under topological deformations, okay? So it gives you a way to test whether two spaces are different, right? So in particular, since this has Euler characteristic 1 and that has Euler characteristic 0, then these two spaces cannot be topologically equivalent, okay? So that's the simple idea behind topology, that you have shapes, you want to understand whether or not they're similar, and what you do is you compute invariants which do not change under deformations, okay? So let me give you a couple more examples. Okay? So let's say that we start with a circle in R2, just x squared plus y squared equal to 1. Let's triangulate it. Boom, that is a triangulation of the space, right? So I've divided into vertices and edges, and I can compute the Euler characteristic of the space. Vertices minus edges plus faces, 0, right? Hopefully 0. Yeah, 0. Here's another space, the torus. The torus, I guess people in physics see these shapes a lot. Well, the torus, you can think of it as the surface of a donut, or just as a circle, Cartesian product, another circle. Another way I like to think about it is as a square that you took and you glued together the bottom and the top in the same direction. That gives you a cylinder, and then this side with that side. Place it together, that gives you the torus. So with this model of the torus, you can triangulate it, and one can check that the Euler characteristic is 0. Okay. Here's another shape that is pretty interesting. It's called the Klein bottle. How many of you know of the Klein bottle? So it's a space, a lot of you. So it's a space, it's a surface which is non-orientable. I've seen on the internet, they sell glasses with this shape, pretty cool. Here's another model of the Klein bottle. You start with a square, and then you do the following identifications. You take the bottom with the top in the same orientation, you get a cylinder, and now the left and right circles are in different orientations. That means that you cannot go like this, because then they would coincide, which means that you have to go into sort of another dimension and then come down inside. That's what this is doing. So in particular, it's a space that you cannot realize in R3 without self-intersections, but you can do it in R4 and R5 as well. with that model of the Klein model, we can triangulate it and check that the Euler characteristic is 0. So we've seen at least 3 examples in not too many values of Euler characteristics. Right? So another example is the projective plane. One way to think about it is take a disk, and we're going to identify the boundary points as follows. Every 2 points that are antipodally opposed, we're going to paste them together. So for example, if you're walking in this direction, then what happens is that you get teleported to this side. Here is a triangulation of RP2, the projective plane, and the Euler characteristic is 1. So I don't want to just give you a bunch of examples. I guess I will. So these are sort of 5 spaces, interesting spaces. And what we can say right away is that the sphere is not the same as the circle or the Klein bottle or the Taurus or the projective plane, right? That's sort of intuitive. It doesn't, the sphere, doesn't have any. The sphere sort of has a sort of a 3-dimensional void in the middle, but every curve on the sphere bounds something that is filled in. That is not the same thing on the Taurus. For example, this curve bounds an empty space. So it makes sense that this is different from all these spaces, but the Euler characteristic is just not powerful enough to distinguish between these 3 guys, and they ought to be different. Okay, so what have we done so far? I've told you what topology is compared to geometry. I've given you one example of a topological invariant, namely the Euler characteristic, and I've shown you how to compute it for simple spaces. Okay? What I'll do now is I'll do a computation without pictures. Okay? So what do I mean? So if you look at a photo, perhaps it looks continuous to you, but if you look very closely, you will see that it's just a matrix, at least a sort of a grayscale image. Each pixel is just a value between 0 and 1, telling you the grayscale. Okay? So that means that small pieces of images, or in general just images, can be represented with numbers, and those numbers can be turned into vector representations, for example, by concatenating the columns of the matrix into one long vector. Okay, so this gives you a way of going from image data to vector data that you can do math with. I'm going to pose a question to the class, since it's the first day. Here's the question. Imagine that I give you the following collection. It's the collection of all 17 by 17 images, pixel images, in black and white, depicting a single dot, a single white dot. The size of the dot is fixed. The intensity of the dot is also fixed. But I allow the dot to move within the image in all directions. You can even move it outside of the image, so you get the black image. Does that make sense? Okay. What is the Euler characteristic of this space? Yes.
With what kind of, just the Euler characteristic invariant, you're asking?
Yeah, just the Euler characteristic. What number is it? Right. So I've shown you examples of, right. So you take a circle, you take a torus, you take a Klein bottle, triangulate them, count, and then you get a number.
I was gonna say 1 then,
You're gonna say 1. Why 1?
because it's a dot. And
It's
so
a
it's
dot.
only 1 vertex.
Interesting. remember that. Okay, let's think about it a little bit. So each image is 1 dot, right? But the dot is allowed to move in all directions. How many degrees of freedom do I have? 2, right? I have 2 degrees of freedom. I can move right and I can move left. So your space is at least 2-dimensional. You have 2 degrees of freedom to control the position of the dot. Okay? So we're dealing with a surface. That should be the set of all such images, a big surface, right? how do you compute the Euler characteristic of a surface? You triangulate it and count, okay? We're not gonna do that. We're not gonna do it here. I actually created a very simple computer program to estimate probabilistically what the Euler characteristic of the space should be, okay? So again, I'm not doing it manually of finding the vertices and the edges and the triangles and counting. I just wrote a computer program to do that for me, okay? And here are the results. Here I'm showing the candidate Euler characteristic, and the height is the probability that that's the right number. Okay? So what we're getting is that the data set that I just described, the data set of all such images, is highly likely to have Euler characteristic 2. Does that make sense? Hopefully, maybe. So what space do we know has Euler characteristic 2 from what we've seen? The sphere, right? The sphere. So the question would be, does this collection of images, again, in some high-dimensional Euclidean space, does it have the shape of a sphere? The answer is yes. And this is the type of question that one can answer with topological methods. The idea of, I give you a data set that you don't know much about, and you try to compute topological invariance, like the Euler characteristic, to try to infer what is the type of space that should parameterize it. I claim that you've done this before. When you do statistics, and you say, I'm gonna take my data and I'm gonna fit a linear model, you are a priori saying that your data accumulates around a line or around a plane, right? What we're doing here is saying, we don't know what the space is that my data accumulates around, so we're gonna compute topological invariance to give us a clue of what it is. Yeah?
Oh, sorry, for this example, you said you write a program for analyze this data set.
Mm-hmm.
My question is, could you analytically analyze these images? And
Yes. Because I mean, there's a way of parameterizing it,
okay.
and you can actually compute it.
Okay.
But what we're gonna do is sort of data oriented. That's what
Okay.
we're here for. I guess the math people in the room can probably think of ways of doing it. Okay, so that's the idea of topology and data, how we use topological ideas to analyze data sets. But as we saw, the Euler characteristic is not a very powerful invariant. There were a lot of spaces that have the same Euler characteristic, and they ought to be different. So what do? You find better invariants. So another invariant that we use in topology is called the Betty numbers. So here's what they do. To a space, it could be the sphere, it could be the torus, or it could be the space of images that we described before. It associates a collection of numbers, beta n's. So what do the Betty numbers measure? They measure the number of holes in each dimension in your space. Let me explain that with an example, or with 2 examples actually. So when n is equal to 0, beta 0, I'm measuring the number of 0-dimensional holes. What does that mean? That sounds weird. A 0-dimensional hole means a connected piece of the space. In other words, Betty 0 measures the number of connected pieces that the space has. So the sphere is completely connected, so Betty 0 should be 1. Okay? What should be Betty 0 for the torus? It should be 1, right? It's a connected space. It's counting the number of disconnected pieces. Betty 1, on the other hand, counts the number of one-dimensional holes in the space. How is that measured? A hole, a one-dimensional hole, is the same as a closed loop that doesn't bound anything. Maybe? take the sphere, right? Draw a closed loop on the surface of the sphere. There is always a spherical cap in the middle of the closed loop, right? Any closed loop bounds a piece of the sphere. Question: what should be Betty 1 for the torus? 1. Who said 1? You, Joe, right?
Yeah.
Why 1 again? 1 again. Why 1 again?
I just like the number 1.
That's-
No, it just seems like because there does seem to be something in the middle of this.
In the middle of the torus.
Yeah, like there's a whole.
There's at least one hole. This one, right? So this is a closed loop that doesn't bound anything. This space is empty, right? I would say that you are close. It's actually 2. One hole is of course this one, as we said. The other hole is this one, because the torus is hollow. So what's going on is that if you draw a closed loop going around like that, say this guy, then in the middle there's nothing. So it's a closed loop that doesn't bound anything. This sounds weird at first, but I promise you it'll make sense in a couple of weeks. Now Betty 2 measures the number of two-dimensional holes in the space. So if Betty 1 was measured with curves, right, then Betty 2 should be measured with closed two-dimensional objects that do not bound anything. So in that sense, the sphere has Betty 2 equals 1 because the sphere itself is a two-dimensional object bound in an empty volume. For the same reason, the torus also has Betty 2 equals 1 because the torus is a closed two-dimensional object bound in a three-dimensional void in the middle. Okay? Those are the Betty numbers. Here's a theorem. The Euler characteristic of a space, the thing that we can compute by triangulating, counting vertices minus edges plus faces, can also be computed as this alternating sum of Betty numbers. Crazy theorem. One can also show that these numbers do not change if you distort your space. They're also topological invariants. And these are actually better invariants, right? Because they look very different for the torus and the sphere. And they can actually distinguish all the other spaces we had at the beginning. Okay. Are there any questions?
So I'm sorry.
Yeah.
What was the reason there was only one zero-dimensional hole?
One zero dimension, yeah. So zero dimension measures connected components. It measures the number of connected pieces in the space.
So there's one connected.
There's just one connected component. Yep. Okay, so I wanna now move a little bit on to the perhaps the topic that brought you here, the idea of data. How do we actually use these ideas to analyze data sets? Okay? So let's say that I give you the following data set. It's just a collection of points in R2. Okay? So let's see if you learned from the previous discussion. What is Betty 1 for this space?
N minus 1.
Say that again?
N minus 1.
N minus 1, where N is
The number of points.
the number of points. Remember that Betty 1 is the number of loops, the closed loops that do not bound anything, right? Betty 0 is the number of connected pieces. Okay? So I'm with you, maybe, that Betty 0 is the number of points, because the points are disconnected themselves. So Betty 1 should be what?
1.
It should be 1. No, it's not. It's 0, because there is just no way of connecting the dots.
Oh, okay.
The dots are disconnected, right? So it's sort of, your brain wants it to be 1 because we see the shapes. Our brains make the connections, but the data is what the data is. Okay? So again, Betty 0, number of disconnected pieces is just the number of points inside of X. We would like Betty 1 to be 1, but it isn't because the space is not connected. You cannot go around. But here's one thing one can do to force the data to do what our brain is telling it to do. One can do the following. Let's say that we have this parameter epsilon that is telling you that if 2 points are at a distance less than epsilon, then we're gonna connect them with an edge. Okay? Now, if you have 3 points and they're all connected with edges, we're gonna fill in a triangular face. Okay? If you have 4 points and you have all the edges and all the triangular faces, we're gonna fill in the tetrahedron. Okay? And so on. So what you will see is that as epsilon increases, and by the way, this was the original data set that I started, as your tolerance epsilon increases, then you're able to connect more and more things. Right? At the beginning, the collection of data points was completely disconnected. As you vary this epsilon, you're allowed to connect more and more things. So hopefully what you will see is that at the beginning, everything is disconnected, but at some point, everything is now connected. Okay? Hopefully what you will see is that there are no loops in this side, but now here there is, for example, this loop and this loop that are not filled in by anything. Okay? So what we can do is we can track this 0 here is meaning to say Betty 0. Is meaning to say, let's measure the number of disconnected pieces of the space. So what we can do is we can track how the connected pieces of the space merge together, right? So at the beginning, there should be as many disconnected pieces as points were in the original data set, and then at some point, there's only one connected piece because all the points are connected. Okay. Does that make sense? We can also measure the loops that are not filled in. So for example, here at this stage, there are 2 loops, namely this guy and that guy. Okay? And then when you get up to this point, those loops were filled in, right? So this guy is now filled in by all of that, and now this guy is filled in by all of this. Yeah, go ahead.
I'm confused. Maybe I'm misinterpreting this. What's the y-axis on these graphs?
Oh, yeah, that's a great question. The y-axis is meaningless here. I'm just saying each one of these lines,
They're disconnected points.
they're disconnected points. In here, each one of these bars is just a loop that hasn't been filled in. The y-axis is meaningless. What matters is the x-axis that is telling you what is the scale at which I'm connecting things. Okay, thank you for the question. This is called persistent homology, and it's a tool that is widely used in applications of topology to the analysis of data sets. So going back to our torus, the surface of a donut, or another way to see it is S1 cross S1. Here are the Betty numbers, as we said before. Betty 0, number of connected components, just 1. Betty 1, number of loops that do not bound anything, I have 2 of those. And Betty 2, number of 2-dimensional closed surfaces that bound an empty volume. These are the bars that I described just now how to compute for this collection of points, right? So I sampled at random these points from the surface of the torus and just saw and computed how the points connected, how the loops formed and then got filled in, and then how the voids formed and then got filled in. And hopefully what you can see is that there's just one long bar here in 0, right? So it's saying that at some point everything got connected and continued to be connected. In 1, what you will see is that there's a bunch of loops that appear but then got filled in, but there are these 2 loops that persist for a while. And in dimension 2, you will see that there is this void that persists for a while. And what you should compare it to is, I have 1 here, 1 here, I have 2 here, 2 there, and I have 1 here, 1 here. So this is a way to measure Betty numbers for data sets which were not connected to begin with. Does that make sense? So this is something that one can actually compute. There's a beautiful Python package called Ripser that allows you to do something like this. Okay? We're gonna see a little bit more about it during the semester. Okay, so thus far, what do we have? Topology geometry, Betty numbers, Euler characteristic. We can measure shape in data. Okay? Let me show you an actual application because this sounds like a bunch of gibberish thus far. So I want to tell you about an idea that I claim is useful in data science. The idea of detecting recurrence in time series data. So here is a plot of how the housing prices in housing markets, how they change with time. So again, the x-axis is just time, y-axis is price. And hopefully you will see that there's a recurrence in the patterns that you're seeing. Why is recurrence something useful to have in data? If you're trying to predict the future, the best position to be in is if that future happened in the past. If you had already observed it, then possibly you can detect it again in the future. So if you can identify recurrence in your data, perhaps that can aid you in prediction. Okay. If you want to train a classifier or a predictor. Here's another type of recurrence that we see. In biological systems, there is something called the Circadian clock. And it regulates things like cell division, when are you tired, when are you hungry. And what biologists know is that this happens at the genetic level. So for example, here is a picture of gene expression. These are genes. The color is gene expression level. And these are the different stages of cell division in yeast. So what they see is that biological processes like cell division in yeast can be seen as recurrent phenomena at the level of genes. Okay? So there is a ton of problems where recurrence detection is something that you would like to do. Okay? Topology, where does the topology come in? So here are a few data sets. I forget I have this, but it's a great opportunity. So here's a bunch of data sets with recurrent structure. So not only numbers, but sort of, this is a sound recording. Perhaps I can play. So that's a horse, but it's part of an experiment to see how the sort of mind state of horses, where you put them under stress, is reflected in their vocal patterns. This right here is a fluid that is being heated up, that you're heating it from the bottom and you're cooling it down from the top. This is called Rayleigh-Bernard convection, and perhaps the people in physics can tell us more about that. So what it is you know, as you heat up the fluid, then you create these vortices and these currents. This is super useful to try to understand what happens in the atmosphere and try to predict hurricanes. This is actually video data from speech sciences right here across the street at MSU. The way they collect this data is by putting a camera through your nose, right? And they put them down the throat, and they tell you, say ah, you say ah, and this is what comes out. We actually used this type of data, and analyzing the recurrent structure, we can tell things in terms of speech pathologies at the physiological level. This is another type of time-varying data set, dynamic networks. So you can think of friendship networks, you can think of cell networks, devices interconnected. So again, you're trying to predict future patterns, and one way to do it is by analyzing the recurrent structure of the time series. Okay, so what is recurrence and how do we quantify it? So here is one idea that I hope to tell you more about towards the end of the course. Is this idea of sliding windows. People that think about dynamical systems are perhaps familiar with this. So what is it? So imagine that you have a time series. Again, it can be just a collection of numbers, that's your time series, or it could be a collection of images, like a video, or it could be a collection of networks, like in a dynamic network. We're gonna fix a window size W, boom, and we're gonna concentrate on the graph of the function within t and t plus w for every t, okay? So this is just a snapshot of the time series in this time. If you were to arrange those snippets of the function according to their similarity, right? So snippets that are more similar being closer, hopefully you can imagine how recurrent behavior in the time series will be reflected by circularity of the collection of snippets. Hopefully I was able to convince you at the beginning that things like the Euler characteristic and the Betty numbers are ways in which we can quantify the existence of loops and holes in shapes. Okay? So that's what we do. So this is actually something we did a while ago for analyzing time series data. So the idea is, start with your time series, as I said before, fix a couple of parameters that are going to tell you the size of the window and how we're going to discretize that window. The discretization step is going to be tau. It's going to be a real number, a positive real number. And d, or d plus 1, is going to be the dimension, how fine I'm going to observe this window. So what I'm going to do is I'm going to evaluate the function. Let's say that I can evaluate the function that gave rise to the time series. I'm going to evaluate it at the points f, t plus tau, t plus 2 tau, all the way up to t plus d tau. Okay? Effectively, what I've done is I've discretized this window of the time series into d plus 1 values. Okay? You can put all of that in a vector, and let's just call that the sliding window of f at the point t with the parameters d and tau. Okay? So what is the idea? The idea is that you can put all of these vectors, I should say it here. Each one of these vectors, right, is supposed to be discretizing one of these windows. So it just gives you a vector of t plus 1 coordinates in Euclidean space. If you change the t, meaning you slide the window, you get yourself a collection of points in Rt plus 1. Each point is discretizing a window. If there is recurrence in the time series, then whatever curve you get in here should look like a cycle, right? Which is again something that we should be able to detect with topological ideas. So this method is called swipers. It stands for sliding windows and one persistence scoring. I'll explain what the persistence is in a second. We've already seen it. But again, the idea is take your time series, do the sliding window technique, and what we do now is compute these barcodes, right? So you remember how we were changing the epsilon, joining things that were epsilon closed, holes appeared and disappeared. So the idea is that if there's a long bar in here, that should be indicative of a loop in the original time series. I'm gonna try to put my money where my mouth is. So this is a data set from biologists at Duke University. So they wanted to understand the circadian clock in mammals. So this essentially, so they do the following. They take a bunch of mice, they put them in a box. Right? And then what they do is that they expose them to light and darkness throughout a period of time. What that does is it synchronizes the circadian clocks of the mice. Then every hour, they take a mouse, take a piece of the liver of the mouse, and do a gene expression panel. Okay? So what you end up with bunch of gene expression values for a bunch of genes across time. Okay, so each row is supposed to measure a particular gene, and each column is supposed to be a time point in your experiment. So I'm showing you here the actual patterns of how the gene expression changes in these mice throughout time. And then what the biologist asked is, can you please rank these genes from most periodic, from most recurrent to least recurrent? Okay? If there were 100 genes, I would ask a grad student, can you please order them? So the grad student would go, people like you, right, earning your degrees, will do the work. There's 50,000 of this. So there is just no way to do that by hand. But hopefully, I was able to convince you that using ideas from topology and sliding windows, one can actually measure recurrence. So let me just show you the results, and we'll go from there. Hopefully it will crash. Okay. Okay, so now these are so what I did is I used this idea of sliding windows and barcodes to measure recurrence in this time series data. And I'm showing you the ranked, sort of the most recurrent genes in the data set. Okay, so hopefully you can see that we were able to actually find genes that behave periodically. If you go down, hopefully it gets worse, right? It degrades. You shouldn't see anything that is recurrent. And that is indeed the case. So why is this useful? So we were actually able to find genes, like these guys, that when a human looks at them, you say, oh yeah, they're completely recurrent. But when you sort of put them through the state-of-the-art detection algorithms that people use in biology, they just don't show up. Because the algorithms that people use are just not designed to find these types of genes. So here's another type of time series. These are videos, right? So a time series, a video is just a collection of images, one after the other. So in that sense, it's a time series of images. Here is a visualization of the collection of sliding windows from this time series, right? This is as recurrent as you can make it, right? It's a very repetitive pattern, and this is how the point cloud looks like. So we did the following experiment. We took a bunch of videos and put them on Amazon's Mechanical Turk. How many of you know what that is? Amazon's Mechanical Turk. Not many of you. Okay, cool. So it's a platform that Amazon has to do machine learning data collection. So essentially what you do is you put a task, like say, is this a cat or a dog? And you pay humans to collect, to say, yeah, cat, like CAPTCHA, right? So CAPTCHA, right? So that's a data collection technique. So we did that. We took a bunch of videos and we pay a bunch of humans. We didn't pay them much because we didn't have much money, but we took a bunch of humans, we paid them some money, and they asked them, can you compare these videos? Here's the actual prompt that they got. They would look at a couple of videos and ask which one looks more recurrent to you. Let me just play a few of them. So that's that. And humans are supposed to be the gold standard in terms of perception tasks when you compare them to other machine learning algorithms. So when we compared this idea of mixing topology with other ideas and compare them to what humans did, we got that the sliding window method is the most correlated with what humans do. These numbers have correlations in terms of rankings. And when you compare sort of not all other, but a couple state-of-the-art methods with what the humans said, the correlation is just abysmal compared to what topology has to say about this data set. What time is it? You know what? Let me go to the end. So the course is about topology and data. The idea that I'm going to exploit throughout the semester is how can we leverage tools from geometry, topology, linear algebra to solve real problems in data science. Okay? So if you go to the following website, you don't have to do it now, but if you go to my website, you will be able to find the link to the course site. You will find something like this. In the website, you will find a description of the course, what are the major topics we're gonna cover, what are some useful references, and importantly, the syllabus for the course. I try to be friendly with the environment, so I didn't print them and write them here, but hopefully you can do that on your own time. I would like to go through the syllabus now to just explain what the sort of structure of the course is going to be. So as we said before, that's me. The website, this is supposed to be a 3-credit course. If you haven't seen what topology is before, a useful background to have is just linear algebra. How many of you have taken linear algebra before? A couple of you. Okay, so just to see that you know what you're trying to, that you know what you need, I would recommend looking at Linear Algebra Done Wrong by Sergey Trail. There's actually another book, I think this is the second one. There's another book called Linear Algebra Done Right. That's for math people. Apparently this guy didn't believe that, so. Linear Algebra Done Wrong. So if you look at the first chapter, you should get what you need. Yeah?
So you don't expect us to understand, you don't have to understand abstract algebra, for example?
No need. It would be great if you did, but no need. So if you have linear algebra, you'll be fine. So as I said before, topology, like geometry, is concerned with the study shape. Hopefully I was able to show you that. And what the course tries to communicate is how these ideas of topology and geometry have made a jump from theoretical mathematics to computational mathematics and data science. So that's the goal of the course, show you how that is done. And here are 4 resources that I think will be useful. The first one, as I said, is the Linear Algebra Done Wrong book by Trail. The first chapter at least. There's a second book, Elements of Algebraic Topology by Moncrief. So people that perhaps are in the math department have seen this book before. It's a super, super friendly book. So if you can get it, it will be super useful. If you want to go a little bit more in depth in these ideas of persistent homology and sort of the algebraic topology that is happening in the background, I would recommend Persistence Theory, From Pure Representation to Data Analysis. It's a recent book by Steve Udo and it's freely available on his website. And then the fourth resource is a book review at the American Mathematical Society on this book and another book. So I think this would be a useful resource just to get a broad picture of where the subject is and what are the tools that people use. What is the structure of the course? I know that nobody likes homework, but it's necessary to really understand what is going on. So I would like to have around 4 short homework assignments throughout the semester. And I guess the important piece in the course is that we're gonna have an end of semester final project. So what would I like to have? The final project is gonna be an opportunity for you to do independent research. So you can be reporting on a paper that was motivated by the topics in the class, or you can be, reproducing a data analysis that has already been done. Ideally, you would pick something original that is in line with your research. So hopefully throughout the course, you can start to think, how do these tools may apply to the problems I care about? So that will be the final project. The final project will be essentially an in-class presentation and a short write-up. It would be a sort of a 3 to 5 page write-up. And I'm hoping that it will be in groups. Okay, so two to three people. So this is the breakdown. Attendance and participation are key. I know that you're shy today because it's the first day, but hopefully you'll get a little bit more comfortable as the semester goes. Homework is going to be 30%, and the final project is sort of the bulk of the work. It's 40%. Then there's a sort of policy of missing required assignments, Spartan code of honor, academic honesty, all the good stuff. So that's it. Are there any questions?
My small question.
Yeah.
I know there's a class, Topology, is offered for undergraduate level. So is that useful or whatever for this course?
The answer is yes. I mean, the more you know, the better you are, but it's not required at all.
Not required.
Not required. They go a little bit more in depth than what we need.
Okay.
Actually, I would like to hear from a couple of you what brought you to this class. So you saw topology and data in the title. Why are you here? Now let me ask you, since you've been asking questions.
Okay. I'm also doing data analysis.
Yeah.
So I'm so except the machine learning classes I have taken,
Yeah.
for example, deep learning and several general technologies.
Mhm.
So I'm very interested how topology used in data analysis.
I see.
That's the reason
So to broaden your horizons.
yes, maybe I can combine this method with some other method. I don't know. That's fine.
Okay. Biomedical engineering, right? Why are you here? I mean, I'm glad you're here.
My project is studying the 3D structure of the uterus.
Okay.
And the
Rip
movement of the uterus.
With rip that? Okay.
How like the structure folds, and we have like two different shapes, structures, and I want to see how I can compare.
I see. Okay. I'm actually investing in that. So that's a disclaimer up front. So, well, how about, yeah, you. Can you tell me your name?
Omar.
Omar.
Yeah, I haven't registered for this course yet.
That's fine. I mean, you're here the first day.
Yeah, so I've actually been a little bit interested in topological data analysis.
What is your
since then.
background?
I'm a pharmacologist.
Okay,
but
cool.
I do computational toxicology.
Mhm.
And an interesting, one of the more interesting things that's come out recently is the UMAP,
Yep.
which has strong foundations in topology.
It does.
And it does a lot of really cool, it has a lot of really useful features. And
Mhm.
I think the more I've read about it, the more it seems fit for transcriptional data analysis specifically, like you showed with the recurrence in circadian rhythm
Yeah.
and gene analysis. And so my own research is looking at single cell data especially in inflammation in mouse livers, and trying to see if I can apply some of the techniques that I can learn from here.
Cool. It sounds like it planted you here.
What?
It sounds like it planted you here.
Oh, no.
But no, of course.
Yeah.
No, thank you. That sounds super interesting. Something I forgot that I should have mentioned is sort of what are the topics. Of course, you're going to see them on the website, but just to give you an idea. So I've divided the course into 3 pieces. A background piece, which is hopefully where we all get up to the same level. There's going to be the algebra we need, in particular fields, vector spaces, linear transformations of the Smith-Morgan form, right? Linear algebra. Now we enter the topological land with simplicial complexes and embedding numbers in homology. I've already explained a little bit of what that is. Then we're going to talk about the idea of persistent homology and topological data analysis more in depth. So this is where the barcodes come in. So we're going to cover the intuition, the actual definition, and how to compute it. And there is an interesting idea, which is sort of the stability, which is what is the resistance of all these techniques to noise in data? Because if you're analyzing real data sets, they're going to be noisy and imperfect. You need to be able to take that into account. I would also like to cover this idea of mapper, which is similar to UMAP in that it's a dimensionality reduction method to visualize complex data. And the last unit, which I think is the more exciting, is applications. So we're going to talk about topology of spaces of microimages. Remember the example of the sphere of the image with one dot. So that kind of idea. How do you analyze spaces of features from ensembles of images? And this has applications to image compression and texture analysis. So hopefully I'll be able to communicate that. I would also like to talk about time series analysis, recurrence in biological systems. Already talked about that. And this idea of hypothesis generation from large data sets using dimensionality reduction techniques. Okay? So that's the goal of the course. So if there are no other questions, we'll adjourn for the day, and then I'll meet you on Wednesday here at 3. We get to go early today.